G'day, Mr. Hannah here. Last video in this little series on differentiation. In this video we're going to be looking at some of the applications of differentiation. Some of the times where this might be used in the real world. And generally there are two types of problems in the real world that we might like to use differentiation for. They're problems that are either involving rates or rates of change. This rates, a key one from rates is motion, something to do with motion. So that's one of them, and the other key time is when you're doing a maximizing or minimizing problem. Maximizing or minimizing problem. Of course, we've already looked at finding tangent lines and normal lines, which may come up as well. So the maximizing and minimizing, might be used in the real world if you want to maximize profits, or perhaps you want to minimize sort of building materials whilst maximizing something else, like how much volume your box has or something like that. So I'm going to do an example of a question that has something to do with the rates, and I'm then going to do an example that has something to do with maximizing or minimizing. Now, a key thing you need to remember about motion is that we have displacement, which we'll call x. Occasionally, some textbooks may also use the letter s to represent rates, to represent displacement. So it might be x, might be s. And displacement will, of course, depend on time. Okay. Now your displacement x will be some function that depends on time. So it'll be kind of written x of t instead of f of x. X of t is like displacement. Okay, so that's displacement. You might also have a velocity. Velocity, which is like kind of speed, if you like, but also with a direction. And velocity v, if you like, velocity v is given by given by differentiating your displacement. So it's dx dt. Okay. Now Newton also wrote v, just so you know, as x dot t. So we had displacement, which is x of t, velocity, which is x dot of t. Then another thing, acceleration. Acceleration a is given by the derivative of the velocity with respect to time, dv to t. So we've got x, then dx to t, then dv to t. Or x of t, x dot of t, and x double dot of t. Okay, you may see some of these different notations coming through. Another way of doing it is if you had called your x of t, if you had all along called that f of t, function of t. Oh, sorry, that shouldn't be there. Let me write that again. F of t. Then velocity would then be f dash of t, and acceleration would be s dash double dash of t. In other words, it's an f dash of the first f dash. Okay, so to get from displacement to velocity, you do a derivative, and to get to velocity to acceleration, you do another derivative, sometimes called a double derivative. Okay, so that's enough explanation. Let's get into a question. So here's one here. It says, a point moves along a straight line so that its distance, which is x centimeters from its starting point, called O, at a time t, is given by this formula. Let me write this formula out a little bit more clearly. So let's say that it's x with respect to t is t cubed minus 6 times t squared plus 9t. There we go, there's our equation. And it's asking us to find at what times and what positions the point will have zero velocity. Okay, so it's all about finding something to do with when it has zero velocity. So we need to come up with the equation to give us the velocity. So we know that the velocity is if you do a derivative of this. So we're doing dx to t here, derivative of this thing, which will be 3t squared minus 2 times 6, that's 12t plus 9. And we're interested in when this thing is equal to 0, and that is equal to 0. So let's factorize it and figure it out. So let's take 3 out as a factor. T squared minus 4t plus 3. Now I can factorize this. I noticed that to get 3, that could be 1 times 3 or minus 1 times 3 times minus 3. And we pick the one that give minus 4 when I add them together. So that is going to be a t minus 1, t minus 3. So I've got minus 1 times minus 3 gives positive 3. Minus 1 plus minus 3 gives minus 4. So here we go. There's my velocity equation. And I need that to equal 0. And you can see that that's going to equal 0 when time is either 1 or 3. Okay, so let's look at our question again. Find out what times and what positions the point will have 0 velocities. Well, we've found the times. The times are at t equals 1 or t equals 3, and those are both in seconds, so I should write seconds there. Now I still need, however, the positions at which the point has 0 velocity. So we need to pick out our positions equation. That's this one. This gives us the position, doesn't it? X of t. And the t times we're going to use are these two times here, 1 and 3. So let's substitute these into our equation. Okay, so we're going to kick off by doing x of 1. So that'll be 1 cubed, putting our 1 in for t, minus 6 times 1 squared. Oops, let's go. Then plus 9 times 1. Okay, so this gives us 1 minus 6 plus 9 equals 4. And that's in centimeters. 4 centimeters. Now let's find our other one by putting 3 in. So this will be x of 3. Gives us 3 cubed minus 6 times 3 squared plus 9 times 3. Crunch the numbers. 27 minus, that's going to be 9, so that'll be minus 54 plus 9 threes, 27, which will give us minus 54 centimeters. Okay, so these are our two positions at which our velocity has 0. Okay, so we've done this entire first question. Tick. Okay, next it asks us to find the acceleration at these instants. So we've got to now find our acceleration equation. Okay, so thinking back to what we looked at the start, the acceleration is the derivative of the velocity. So here's our velocity equation, and we need to find the derivative of that. So our acceleration is dv dt. So here, let's use this one in fact. So 3 times 2 is 6, t to the power 1, and minus 12. And the 9 becomes a 0. So there we go, we're done. And it wants us to find what the acceleration is at the instance from the previous question. So the times for the previous question are 1 and 3. So let's find the acceleration at time equals 1 is 6 times 1 minus 12. So the acceleration there is 6 minus 12, that's minus 6. And that's in meters per second squared. So what that means, and minus a negative acceleration means it's slowing down. Okay, interesting. Now find the acceleration when time is 3. So 6 times 3 minus 12 gives us 18 minus 12, gives us positive 6 meters per second squared. Okay, so positive acceleration, that means it's speeding up. Alright, so that's all of part B done. Now looking at part C, find the velocity when its acceleration is 0. Okay, so let's use our acceleration equation, this one here. that now it needs to equal 0. So let me write that out again, right out over here. So the acceleration with respect to t is 6t minus 12, and that needs to equal 0. So give us 6t is equal to 12, so t must be equal to 2. Okay, so our time is 2, and now we actually need to find the velocity at that time. So we need to find the velocity at time 2. So let's put that into our velocity equation, this one here. Okay, that's our velocity equation. So let's put 2 into that. So we've got 3 times 2 squared minus 12 times 2 plus 9. Okay, that here gives us 3. 2 squared is 4. 3 times 4 minus 12 times 2 is 24 plus 9 gives us 12 minus 24 plus 9. The 12 plus 9 gives 21 minus 24 equals negative 3 meters per second. Okay, so it's actually going backwards at this particular point when it has 0 acceleration. So it's not slowing up, slowing down, or speeding up. So there we go. We've done all 3 parts of that question. Now, if this was the first time you've seen one of these questions done, I imagine that was quite confusing. So I'd recommend having a rewatch over that video a couple of times whilst you're trying to do questions similar to that yourself. Okay, that might help you figure out how to do them. Okay, so that's part 1 done. So that was our rate part, and we looked at using differentiation to think about rates of change and applying that to a motion situation using displacement, velocity, and acceleration. Next up, we want to be thinking about a maximizing or minimizing style question, of which there's quite a number going to be coming up for you. Okay, so here's our maximizing problem. Now, fair warning, I've just made this up, so who knows what sort of answers we'll get. Alright, it is a very classic problem though, and you'll absolutely, definitely get one very similar to this. Okay, here we go. It says a rectangular piece of cardboard is to be made into a box as shown. Here's a rectangular piece of cardboard. It's got a length of 10 centimeters, width of 8 centimeters. You're going to cut out these little corners here with little square corners that measure X. And when you fold it all up, it'll create this box. Okay. And the question is, find the value of X that will give the box the maximum volume. Okay, so we want to maximize the volume of this here box. Now when we fold it, we're going to get whatever this is as the width here. Let's just call that W for now. That'll be the width of this box. And the length of the box is going to be whatever that is there. Let's call that length L, the box. And the height of the box is just going to be the length of one of these X pieces. Okay, so the volume of this box is given by length times width times height. And let's substitute little bits in. So the height of this box is just X. It's the piece we cut out. The width of this box, well, it started off as 8, and then we cut 2 bits out of each one being X long. So it's 8, take away 2 of the X pieces. And the length started as 10, but then we cut 2 little pieces of X length out. So that's 10 minus 2X. So the volume of this box is given by length times width times height. So that's 10 minus 2X times the width, that's 8 minus 2X, times the height, which is X. Okay, that's the volume of our box. So let's expand this out. So here we've got an equation, there's a volume, and it's in terms of X. Let's expand this thing out. We've got 10 times 8, 80. 10 times minus 2x, that's going to be minus 20x. Minus 2x times 8 gives us minus 16x. And minus 2x times minus 2x gives us plus 4x squared, and all of that still needs to be multiplied through by x. So write this out again. We've got 80x minus 20x squared minus 16x squared plus 4x cubed. Now let's rearrange it and combine the like terms to get our final equation. Our volume of x is 4x cubed. Now I've got some x squared terms here, the minus 20x and the minus 16x, so that gives us a minus 36x squared and plus 80x. Okay, so there's our equation for the volume of this box. And you can see that it is a cubic function. Okay, so just out of curiosity, let's actually graph this cubic function. Let's define it. So I'll call it v. Why not? V of x. Okay, and it was 4 times x to the power 3. Now I've forgotten. Minus 36x squared. Minus 36x squared. Now was it plus 80x? There we go. Alright, let's have a look at what that looks like by plotting it up. So let's plot our function, f of x. Oh, there it is. Doesn't look too much like a cubic though, so let's zoom out to make sure that we have all of it. Zoom out. Oh, whoops, I understand what I've done wrong. Hopefully you can see my error is that I actually called it v of x, didn't I? Okay, there we go, that's much better. Let's zoom out from that thing a little bit. That'll do. Okay, so here's our function. Now we want the maximum point of this function, which is all the way, whoops, up here. This is the point we're looking for. That's where our volume is maximum. So let me just quickly sketch this function out for us. Where am I? Okay, so our function looks like this. This is our volume axis. And over here is our x-axis. Now it looked something like this. Something along these sort of lines. Okay. Now obviously the maximum point is what we're looking for. The question says that we want to give the box maximum volume. So we're looking for this point here. Okay. Now to find that point, hopefully you remember that to find any turning point, we set the derivative to 0. So we want to find v dash of x, and then we want to set that to 0 to figure out what x is. Okay, so for the first step, we need to find our derivative function. So looking at our volume, it's way over here. Let's find our, maybe I'll do it just underneath. That might make it easier to follow what's going on. So 4 times 3 is 12x squared minus 36 times 2 is 72x plus 80. So there's our function, and we want to set that to be equal to 0. Figure out what the answer is to that. So here we go, we've got 12x squared minus 72x plus 80. And we want that to be equal to 0. So at this point I'm just going to use the cas. I'll be doing solve and this v dash of x bit here equal to 0. Find what x is. I could do this by hand, but that would take a bit of effort, so I'm going to be a little bit lazy here. So let's go back to the calculator page, use our solve function. Algebra. solve. Now I could type it all in, but I'm just going to be lazy again and write solve. Now calculus, find the derivative in terms of x of our function v of x. And that's equal to 0. And I want you to tell me what x is. Now make sure all your brackets are in the right spot. Okay, so it's the derivative of this stuff, and the comma x comes right at the end. So here we go. We've got two possibilities. X will either be this value here, or perhaps x will be this value here. Okay, now let's actually find out what these values are in terms of a decimal. So we'll approximate that. There we go. X can either be minus 1.47 or x can be 4.52. And we've got to decide which one of these it really is. Now, we can kind of cheat by having already plotted this function and knowing that the first turning point is the one that's the maximum, and the second one down here is actually, oh, where is it? There it is. That's actually a minimum. And not only that, but it gives a negative volume, and a negative volume doesn't make any sense at all. So it clearly must be that first one, the 1.47 one. So let's jot this down. So we've solved it. We've figured out that x has to be 1.47. And I'll jot the other one down too, just for a sec. Or x could be, what was it, 4 point something? Let me jump back. 4.5 something or other. 4.5. Now, we cheated, so we know that the first one's going to be the correct answer because we drew this graph. Now, there's another way to tell that this is going to be wrong. Okay, that 4.5 clearly can't be it, and it's this. If this distance here was 4.5, and so was this distance, well, together those two little bits would be 9. Okay, so that bit there, if that was 4.5, and that bit there was 4.5, then this bit and this bit would be 9 together, but the whole length is only 8. So you can't have 8 take away 9. That gives a negative number. So that is not physically possible. You can't have x be 4.5. It just doesn't make any physical sense. So our answer must be this one here. Okay, so now let's read the question again to figure out if we've answered it or not. So the question was, find the value of x that would give the box maximum volume. So here's the value of x. There it is. Now, everything's measured in centimeters, so our answer we need to give also in centimeters. So we need to say that x is 1.47 centimeters. Okay, now we've done everything that this question has asked us to do. So we are finished. Oops, let's get rid of that. We're finished, but it's possible that the question would have gone on to ask us what is the maximum volume. What is that maximum volume? What is it? So in other words, we know that it happens at x equals 1.47, but what is it? So we're trying to find the volume. It's in terms of x, but we want to put our value of x in there. So it's the volume of 1.47. So we can put 1.47 in for our equation. This equation here, put it in, and find our answer. I'm just going to do that bit on the CAS. Phi of our 1.47, and maybe I'll use some of these extra decimal points to be a little bit more accurate. There we go, 52.5 roughly. So the maximum volume is 52.5, and that must be centimeters cubed. Everything is in centimeters, we're talking volume. So 52.5 centimeters cubed is the maximum volume, and it happens when we cut out 1.47 centimeters from each of the corners. So there you go. There's a fairly typical maximizing problem. Just like I said with the last example problem, this might be pretty new to you, so I'd recommend having a go at one of these yourself and then coming back to this video if you get stuck. All right, best of luck, and I'll leave you there. Hannah out.